Okay, so that's the last example right here of what is that we're supposed to do when we go to high dimensional spaces. And we still want to do the same thing to begin with, geometry and measuring distances between points. So naturally, the algebraically speaking, it is nothing but a string of 40 numbers. Okay, so on the left you see them; they're not entirely. You have only can see 18. So suppose that they are 40, and then naturally, the easiest way how to visualize a string of 40 numbers is to put thinking of them as a sequence, and they're just plotting it. So it's quite literally Excel. This is Excel, as you can see, right? So the green column is visualized as this curve, and the red one is the as a red curve. So naturally, they only form a curve because they've been chosen in such a way that they would. Okay, so there is behind, you cannot see it here, but naturally the F and G columns have a formula behind it. That's where the numbers come from. If you pick a general point at random, the red dots will be up and down in a random way. And so you won't recognize a curve there, but nonetheless, it's the same thing, and the computation is the same for those three ways to compute the distance. Once again, some of the absolute values of differences, some of the squares of the differences in square root. That's the Euclidean distance, L2, and then just take the maximum. Okay, so once again, probably the picture at the bottom is it provides the foundation for that measurement for either Euclidean or taxicab metric, either way. So you have to compute those. You take the difference first with the absolute values. Okay, so the one function is bigger than the other, it makes no difference, right? So then it becomes vice versa, it makes no difference. You take all of the differences, take the absolute value, so you end up with a sequence, once again, the purple sequence of positive numbers. And then you just decide what you want to do with it. You can pick either, once again, three ways. You pick the maximum for the last one, you just add them together, okay, so for the first one, or you square each of these and then take a square, add them together and take a square. So that will give you the Euclidean distance. Okay, so just a starting point of how we can do it in a multidimensional spaces. Okay, so I hope this helps. So these are the computations. This is 3D also we looked at. Here's just a few more examples of what you can look at. For example, measuring distances between movie recommendations. It used to be big. I remember Netflix tried to figure that out, and they pretty much failed more than 10 years ago. So if you have preferences about the movies, right? So giving them stars, right? And then what happens is there's a new movie, and they just need to decide to recommend or not to recommend that movie to you. What do? They compare it to other people who have watched this movie and then recommended it. Okay, so then you need to determine whether or not these people are close to you in taste or not. So their taste of movies are compared to your tastes, customer P, customer Q, and then decide whether it's close or not. If it's close, they also recommend it to you because they use in that way they're similar. Okay, if you're farther away, they don't recommend. Okay, so that's the logic of that thing. And as you can see, as many movies as you have, that's how many numbers you have to deal with, and therefore, in a way, you're computing the distance between these, I would say, 1,000 dimensional points. For points in 1,000 dimensional space. Okay, so once again, it's very, very complicated, and the stars, these are not real numbers, so there is issues there to worry about. But naturally, that's a starting point of at least where you could start with a thing like that. So recommendation of movies or music or products. That's how you might be doing it. And naturally, you cannot really do it without a good infusion of probability and statistics into this, but nonetheless, that's not what we're doing here. And you cannot really study statistics and probability without understanding high dimensional spaces. So just as well. So you can go from linear algebra will help you with both multidimensional calculus as well as any kind of probability statistics that you might encounter elsewhere or decide to pursue. And this is once again the what I mentioned before, the patients, and they make different measurements of them. And once again, a course of treatment might be similar to that person, that this person, if their vital statistics is similar. Okay, so once again, the multidimensional space, you want to measure distance there. Okay, so just read these for more examples. Okay, so once the geometry is established in multidimensional spaces, then we can produce certain things that are analogs of what we have had in lower dimensions. So starting with already had a line. Line is you can have four-dimensional space, there is still a line in it. But that's more algebra. If you concentrate on geometry, then you can speak of a circle, sphere, hypersphere. Meaning what? They're just points, say 1 unit away from a given point. Okay, so naturally that's the similarity also. Just looking at, even if you just concentrate on the world that you see, understanding the similarity between the circle and the sphere is quite interesting. It is what do they have in common? They have all the points, say 1 unit away from the origin. Okay, so if you're in two-dimensional space, you have a circle. In three-dimensional space, have a sphere, and then you go on once you write it out in algebra, right? So what you write here, x in say Rn, okay, and then a distance from x to 0 is say 1. That's a circle. That's your circle. N is equal to 2, you have a circle, and then n is equal to 3, you have a sphere. And then n is equal to 4. Well, is there a name for it? No, but it is certainly something that you want to contemplate and have like a building blocks, whatever you want to do in high dimensions. Okay, so all right. So Newton's law of gravity, I would encourage you to read it if you are more into science and physics. So once again, multidimensional algebra and geometry. And as you can see, the force is proportional to the inverse square of the distance to that point. Okay, so that multidimensional distance, but this one is definitely Euclidean. So let's be clear about it. Okay, so that's the formula. Linear regression, another very important example of application of this high-dimensional geometry. So we have collected in data points. Okay, so maybe once again, observations and experiments, one quantity depends on the other quantity, maybe the relation between temperature and pressure, whatever, and especially if it's not something as tangible as physics, especially when its experiments are not possible. So a relation between different quantities that you have established, and then what you're looking for is to find that relation. Okay, so anybody knows what I'm talking about?
A little bit of linear regression.
Yeah.
Using like machine learning models, that
Right.
sort of thing.
Right. So once again, people produce numbers, you collect the numbers, but then when you plot them, it is just a cloud of points. Okay, so if you want to maybe start to conjecture there is some kind of law of nature there or pattern there that people behave in a particular way. So, and you don't want to really go into statistics too much, then that's what you do. You try to approximate that a bunch of points with a straight line. If you look at it, maybe it's there. So this is so how many I have here? Maybe 20 points. And naturally, this is the whole picture right there. And that, by the way, is done for you by itself. So you have points and they do a little linear regression. You tell them it gives, you use this. So blue points is the data, red line given by itself. How does that happen? Well, you can see that there are infinitely many options for choosing that red light, and you choose one of them on what ground. So you have what you do is so M and B are the as you know slope and y-intercept of that straight line. So these two numbers have to be found in a way that is optimal. But now, what is optimal? And the answer is in pretty much the same way as we have done before. So we imagine that these points actually lie in that maybe in this case 40 or 20 dimensional space. Can't quite tell how many. And then compute the distance between those points, and that line is what we are trying to minimize. Okay, so once again, these are the points, and then and we could compute in this case the total vertical distance is we attempt to minimize. There is so once again, forget about the multidimensional spaces. Well, let's just look at this picture and see how the idea reemerges from this. So once again, these are the points, x's and y's. Okay, and then what you do is you are for each m and b that what characterizes the straight line, you carry out this computation. Okay, so in other words, the y that we have and the y that we get. Okay, so we plug in. Where's that? I don't think I wrote it here. So y, no, I did. Right. Okay, so y's. This is the data. So lowercase y is the data. Okay, and then this. No, this is supposed to be. This is supposed to be a y uppercase. Okay, so let's typo here. So once again, for each choice of m and v, you'll have a different collection of y's for these axes. So we do nothing with the axes. And these axes will produce y's, uppercase y's, as the way it's supposed to be. So these are the red ones. Okay, so these are the red ones. So these are the blue ones. Okay, so these are the red ones. And so y's and x, upper and lower case y's have to be compared, and the total error is to be minimized. So the difference is naturally, I have a picture here, maybe not, but you can tell that what's crucial here is this. This is the distance from the line, so the error is in green here. Okay, the distance from the line to the point. So naturally, if I draw a line like this, that would be really bad. Okay, so the errors are very large. So but how do we practically do it? And then that's how. So these are the errors. My approximation, my straight line hypothetically is supposed to produce a perfect alignment, when actually it's never perfect. So when then we take the errors, they're really not errors, the errors, quotation marks. We compute these, and then you decide what you want to do with them. And so here we decided, somebody decided to take the total vertical distance from the line to the points. Okay, and add them together. So naturally, we already know what it is. It's U1, the taxicab metric. You could choose just as well Euclidean, which is L2. So this is L1, right? L1, and this is you can choose L2. And which one is better, and which one is actually practically? Right now they don't really. Excel doesn't tell you which method they choose, and there are many methods. Once you have two, you realize that there are infinitely many methods of doing this. But this is linear regression. It means well, actually, by the way, what's the advantage of L2? In what sense L2 is better than L1? And the answer is surprisingly differentiability. There are no absolute values in the Euclidean metric because the square root looks complicated, but also assures that there is the function itself is actually smooth. This function is continuous but not differentiable. That's the absolute value. It gives you the cusp at the corner at the bottom. And so that if you were to produce some formulas, and you do need to produce the formulas in order to carry it out, then carry out certain computations, because I only pointed out what we're supposed to minimize. How? So the question is now minimize, and the question is how. Okay, so you can minimize L2, you can minimize L1. Okay, so these two matrices, and then how? That's the second question. Okay, so that's a separate question. We just point out how the idea of I mean, so the data, this is two-dimensional, let's face it, only two quantities. Nonetheless, the more data you have, the higher dimension that you have in which everything is happening. And we indeed these two ways to compute distances emerge as a choice for you to make. Okay, so you want to minimize the total distance between the line and the points, and then you create this number over here in the middle, and then you decide, and then you realize if you have had you realize this is actually the taxicab metric. Okay. Okay, so what's right? The formula for the function should be minimized. Okay, so fortunately, once again, to be clear, we're not minimizing the y's. y uppercase. They are unknown, but they are determined by m and b. So it is actually a function that's to be minimized. It's just a function of two variables. Okay, so naturally minimize that, which means that calculus 1 is not going to do it for you. You need calculus 3, function of two variables. Okay, so try to examine it if you want to, but so we will just point it out that that's what is to be minimized. Okay, so moving on to vectors. Okay, so we've seen a little bit of vectors already. But with our understanding of what Rn is, we can start of points in Rn. If we understand them somehow, we can start thinking about vectors very quickly, because after all, 2 points will determine a vector between them. 2 distinct points, or not distinct necessarily, will determine a vector between them. So if you are want a kind of more tangible analogy, you're moving through this n-dimensional space, and then every time that you are thinking about displacements, sequence of points on the left, right? So these are the points, and then these are the vectors that connect them, and so points allocations, and vectors are the displacements. Naturally, if you want to divide later on by delta t, and then you'll have velocities instead of displacement, but that's not a big deal. And then the algebra emerges right there, right? So you have a sequence of displacements, and then if you want a total displacement, that you add them together in this manner. Once again, head to toe. Remember addition of these vectors. Okay, so the vectors 2 points determine. At this point, things become more and more abstract, because even though I'm still visualizing them, but I'm using visualization from lower dimensions. I am speaking of Rn now, n-dimensional spaces, and so that everything has to be as specific as this. So P and Q are 2 points. Then the vector is PQ, just an ordered pair, literally. So you just write PQ. Okay, so this is it. So once these 2 are given, you just write PQ. Okay, so that's your vector. So for now, the coordinate system is present there, because the points depend on the there is nothing else. So I'm going to point out that in a minute, but there is nothing but in high dimensional spaces, there is no such thing. We're not seeing it. There are nothing but strings of numbers. Okay, so we'll get to that later. But for the time being, suppose we already have the points, and now from the points we start create vectors in this manner. Except we are doing it in the manner. Remember, from we're going from P to Q is not the same for QP, and then realize that probably they're just negative of each other. So all the things that we have done in dimension 2 and 3, well, they emerge here from the algebra that we know. Okay, so all right, so then once again, if you were to think how we connect points and vectors, that's how. So old location plus this, which is a point, plus displacement gives you the new location. Okay, so that's the algebra that mixes up points and vectors. Okay, so then so P plus PQ is equal to Q, which means that Q minus P is the vector PQ. Okay, so and then to make our life easy, just as before, we decided to shift everything towards here. Where is it? Shift everything to the origin. Otherwise, every point in Euclidean space has a vector, because from any point P you can move to any point Q. Okay, so I have that thing here. It's like this. Okay, so any point that which makes life too complicated. And instead, we're just choosing one point, and we choose P to be the origin, and only a vector originating from the origin are counted, okay, as vectors, because we can always move. It's the same vectors, identical copies of those vectors around P, around Q. So if we have one that collection, we can move it anywhere we want, and we can do also algebra with them. So that's there is no loss there. So if we have both, then we have if we have every point like this has a collection of vectors, or infinitely many vectors in all directions in it, then we would call it the affine space. And then if not, we call it a vector space. So about that in a minute. But first, once again, that's what happens. once again, algebra of vectors. So in dimension one, it is nothing but algebra of numbers. You attach one vector to the next, and then the endpoints in beginning of the point and the endpoint are. So this my R is right here. The typo once again. So and then you just go from the initial point to the end point, and that creates a new vector. And then once you come up with that plan, so addition of two vectors is executed by attaching the hat of the second vector to the tail of the first vector. Okay, so once it's written, you can use it in any dimension beyond one, and so this is in dimension two, right? At least it looks like two. So attach vectors head to toe, and then go from the beginning to the end. That's your addition. No need for coordinate system. So as long as you know what vectors are, that's how you execute the addition. When the thinking is in terms of displacements, especially, that's very transparent. So these are locations on the left, displacements are the vectors, PQ, QR, RS, and ST, and then you are progressing from point to point to the next. How P plus PQ gives you Q, that's where you are, then Q plus QR gives you R, and on until you reach the point T on one hand. And then that's what, but we are not stopping here. So we want to make things simpler and kind of exclude points as much as possible and concentrate entirely on vectors. And that's what happens here, right here. So instead of doing this, point plus vector gives you a point, then another vector, another point. How about we just take those vectors together? That's what happened here. And so I'm going with exactly what the picture shows, except for the names of the points. PQ plus QR plus RS plus ST is evaluated to be this is, what is this? PQ plus QR plus RS plus ST. Like I said, it's same pictures here, also 4, except the name of the vectors don't match. But other than that, it's exactly the same. So the beginning is there's a match. So the addition is legitimate because there's a match here: Q and Q, R and R, S and S. Okay, so that's heads and toes. Okay, so once all the heads and toes are taken care of, we're left with the beginning and the end. So the answer is T. Yes. Okay. So as you can see, we don't really need points in order to carry out addition. Once again, the picture shows that clearly. So it doesn't matter where those vectors. That these are actually points there, and we're not doing algebra with points. It's just a way to introduce vectors as displacements. So locations, displacements, and then maybe velocity. So incidentally, what you do in calculus too, you have your function representing location, and then what do? You do velocity, the derivative is the velocity. So this is kind of similar. So then if you know where you are, what you do, you take those displacements or velocities and add them together appropriately to produce the total displacement. Okay, that's what the total displacement is. Total displacement. And then if necessary, you add to the initial location, which is P plus PT will give me T, right? So you jump from that if necessary, but really what we're trying to do is minimize the importance of points and concentrate on vectors as much as possible. Okay, so that's just another formula for the same thing. Okay, so you can see how cancellations are happening and why they're happening. So head and toe are shared here. If you write in terms of the vectors, that's what happened. So x1, and then you see x1 again, and they cancel out, and the end result is these are what's left. So this is one, all of these are excluded, and you end up with the beginning and the end, x0 and xm, and that's your jump from that's your vector from x0 to xm. If you look at the points, it's the same thing, by the way. It's the same thing right here. Okay, and then there are cancellations, a literal cancellation this time, right? x0 actually. X1 actually reappears here, and then X2 reappears, and then once again you have the beginning, the end minus the beginning. It gives you the whole trick. So once again, this is the picture. Naturally, summation, sigma notation is becomes more important once you go to high dimensions, so you don't write these dot 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 things all the time. But with a sigma notation, that cancellation would not be as transparent as you can see. Okay, so adding construction. So once again, we already I brought it up some time ago. Once again, vector addition is the alternative vector addition. What we start here with a head to toe. The other one is toe to toe. If you or rather they start at the same point. So remember the idea of we're going to shift all the vectors to the same location. As if they were forces, but they don't have to be forces. Forces usually apply to the same object, and so that's why we add them so easily. But with velocity, sometimes you can have the similar interpretation. So there are two velocities that are applied that are kind of independently present, come from different sources, applied to this boat. So one is the flow of the current, and the other one is your rowing. Okay, and so these two efforts, not forces, but velocities are combined. So literally, you know how much you are put into your rowing, and you know what in a still water how fast you're moving. So that's the velocity. And then the other velocity, literally, you can measure the speed of the current, and then these are two numbers that they, because of the different direction, they interpret it as vectors. Okay, then blue and red. And then if you actually know which way you're going, you have to add these together appropriately. And the addition, as you can see, is this kind of remember what's called parallelogram addition. Okay, so in contrast to the triangle addition, which is what we also have seen. So the forces, once again, the forces are very easy to understand, but these are maybe not so much. So displacements are also possible in the sense that as if you naturally, if you are rowing and you are in the current. Okay, so that's your actual trip is in green, number 3. You're going diagonally. But also imagine that you can actually split your trip into two. You are what? You are maybe you are in a boat. Okay, the blue one is you're in a boat without rowing. Then you go with the flow for 3 miles. Okay, and then you're crossing and then, well, for whatever reason, maybe the current stops, or you just decide to cross on the bridge. Doesn't matter. And then you cross at the same speed across the canal at the same speed as you were rowing. So that way you can actually alternative interpretation of your trip is, in fact, there are two more. So once you get crossing and then flowing or flowing and then crossing is the same as if you were doing rowing and in the current. Okay, the green diagonal. So addition works out perfectly well in dimension 2 as it is in this case. And then there are two constructions. Once again, triangle construction. Either one of these, you have two triangles right away there. Well, number 1 plus number 2 gives you number 3. And head to toe that we have seen already. So head to tail is the triangle construction. So that's my triangle here. If you wish, this is my triangle. Or it is the other one is the parallelogram construction. So this is my parallelogram construction. Okay, naturally produced the same way because after all, the parallelogram is split into two triangles, and so those are the two triangles. And you can move easily around those vectors as we are willing to, as if it is the flow in parallel, and that's why we want parallelogram rather than any other shape, because that way that's what happens when we start shifting the vector. Okay, so if we are once again two vectors, red and green, A and B, we want to add them together, then there are two options, but they are ultimately identical. Either we bring them together into the same source at the bottom, or we do head to toe, which produces a triangle, right? So we complete a triangle. We have two sides, and then we complete a triangle to produce a triangle, and that is the missing part side of the triangle is the sum. Or I do what's on the bottom, I bring them together, and then I build a parallelogram. Okay, naturally, if I build a parallelogram, but then I go diagonal. Okay, I go diagonal, and that diagonal is the same as the side of the first triangle. Okay, so that's the same is the same addition. Okay, so it involves some moving of the vectors around and in a parallel fashion. Okay, so that's once again, remember that in that affine space, we have a vector attached to every point and we can move them freely. And so it's entirely your choice then to do it this way or the other way. It makes absolutely no difference. It's only an application. So the first one more applicable to displacements, and the second one is more applicable to forces. But both of them are vectors, and so it is mathematically speaking, there is no difference. Okay. Okay, we already seen this. Okay, so the names. So once again, I'm trying to exclude points as much as possible. In which case, what I do here on purpose, I'm renaming the vectors. So instead of having two letters indicating the 2 points beginning and the end, I just call them A, B, C, and D. Okay, and so then the algebra will be better in what sense? It's as if the algebra of numbers look at it. There's no difference for us to worry about in terms of what is that PQ? Okay, so is it PQ or PP? Are they attached to each other? Maybe it's multiplication or something, or some weird questions might come up. So just if we do algebra with numbers and we give every number a name, one single letter name. So we could just as well do it the same as that's what I do here. So then these vectors are the picture now is has caught up with our algebra, and so I'm adding vectors A, B, and C, D, and then the end result is the red vector, which is once again A plus B plus C plus D. Okay, so just it takes a little bit of work and get used to it so that you would be treating vectors as if they were numbers. Okay, so because all the rules apply. That's the good news. If whatever you write with vectors, if it only makes sense, any sense, then you can do algebra as if they were numbers. Okay, so what we don't do is with vectors, we don't multiply them for the time being, for sure. And so, but otherwise, addition, subtraction, moving fast stuff around from left to right if you solving equations, all of that applies. All of that applies. And that's why, and we want to use this, you stick with this analogy as much as possible, so that once again, the intuition, the skills that we have developed for numbers, we want to have them used for vectors as well. Okay, so and this is also an important switch that we're making: the geometry, Euclidean geometry on the right, on the left, and the vector algebra on the right. Okay, so that's so you've seen a lot of even in this class a lot of Euclidean geometry. So triangles, angles, and then you have a bunch of theorems about them with electrical triangles, this triangle, that triangle, trigonometry, and then but this is what we do, and that's a big deal. To now they look at pretty much the same picture now is instead of 3 points P and Q, we're now thinking about vectors, and now vector A from P to Q and the other vector from P to R actually added together give you the third side, and then we go PR and we call it AA plus B. One advantage is that you could actually have a picture here, but you can add vectors that have happen to be parallel, which means that there is no triangle. Okay, so I could do this, and then I add these two vectors produced together. Okay, so it still makes perfect sense. So it's kind of a degenerate triangle. Nonetheless, things make perfect sense nonetheless. Okay, so all right. So then, as I mentioned, so that's the way to translate all these into vector algebra later. Okay, so this is the plan. But a bit more about algebra. We can subtract vectors as well. Okay, so if you have two vectors and we know how to add them, what if we want to subtract? Naturally, the understanding of algebra is very important. Where does subtraction come from? This is where subtraction comes from, whether these are numbers or not. So there used to be no numbers. Remember, there used to be no subtraction. There used to be numbers were invented. People started to count. Then people started to add. And they done a lot of addition before they realized that sometimes you have to go backwards. And they came up with they call it a new operation. He gave it eventually symbol, and they learn how to do it. But ultimately, it is derived. It is fully defined as what you see in the box by means of the addition. So if you understand addition, then you understand subtraction. Okay, so that's all there is. So what is the meaning of a minus b? Well, it is a vector or a number that makes no difference, such that b plus c is equal to a. It is, remember what the proper word for it? So what is it? Adding b here and subtracting b. What's the relation between these two operations? What do we call a relation between operations like this? One operation undoes the effect of the other, which is the point why we made it up.
So you're looking for inverse?
Inverse, yes, the word is inverse, right? Okay, so naturally in linear algebra we don't go into other inverses like square and square root, sine or cosine. So we're not concerned with that. But nonetheless, it's worth pointing out that's how subtraction emerges. And so once again, once we have defined addition, this is addition is defined. So once it's defined, then the meaning of subtraction is defined too, right? Like this. This is what's in the box. And then if you still wanna have a picture in kind of a shortcut for computing differences, that's how. Okay, so instead of going diagonally, two vectors are aligned at the beginnings, and then instead of going backwards, but going diagonally, this is how you go, right? So you need to. So A and B, red is A, B is green, and you're supposed to, what's supposed to be produced, look at the formula at the top, B plus C, C is what we're looking for, the C is here. Okay, so we need to find a C, so where is C, such that B plus C is equal to A, so B plus C is equal to A. That's the question, that's the question that needs to be answered. It's literally an equation. Okay, so we have an equation, b plus c is equal to a. We need to find c. Looking at the picture, and the answer turns out to be on the right. So b plus c is equal to a. How do I get an a from b? That's the only way to do it. Okay, so that's where subtraction comes from. Okay. So good news is also not only that, you realize that if here's the and at which point you shift it back to the origin. So the three vectors are actually at the same place. Okay, so and then by the way, in what we're going to do in a minute is the coordinates. Look at what has happened to the coordinates. I was not using the coordinate system to carry out this computation. That they are irrelevant. It's entirely on a piece of paper with no grid whatsoever. I can carry out this what I just did. As long as I understand addition, I can understand also subtraction now. But you can also see nothing special has happened. Subtraction, just like with addition, you add components. With subtraction, you subtract components. Okay, so everything is quite predictable in that sense. But let's continue on and continue ignoring the grid for now. Okay, so the zero vector is a vector from point to itself. Okay, so zero vector, and that's once again there are challenges as with that the idea that we want the analogy between numbers and vectors, and that naturally that's a dangerous step because it might be confusing. This I'm writing the same symbol zero but it's not a number. Okay, so that's a zero as a vector, which is not the same as zero as a number, because zero as a number is involved in a number of other operations. So you can if the 1 plus 0 certainly makes sense, right? But this when 0 is a number. If 1 plus this 0 is a vector, so it cannot be involved in operations with numbers in that manner. So be careful about that, especially when the two different categories of objects are involved together, and they do. So numbers and vectors are intermixed. And then we have algebra of vectors here and algebra of numbers there, and they also intermix. So we have to watch out and be very clear about which one we're using. So sometimes that's why you frequently use to distinguish, you put an arrow above the vector, so there will be no there would be no confusion about it. So as you can see, 1 plus 0 is equal to 1. Well, so with numbers, okay, but it turns out that 0, the vector, serves the same purpose. P plus 0 is equal to P. Okay, so as well as A, well, in this case, I probably go with A plus 0 is equal to A. So these are P. Here's the points on the left, on the right. A is a vector. Vector plus vector is equal to vector. Okay, so this is the analogy once again. So those properties, how do we build this analogy into something more tangible? And the answer is just watch out the properties that we know from algebra. We have to write them up, by the way, and then see if those properties are matched by the properties of vectors. And the answer is they do, at least to the extent as we are so not a number. As we care. Okay, so that's addition. Okay, so that's for as long as addition is there. Okay, we know how to do it as well as subtraction, just in case. And then now this is scalar multiplication. So you can, to begin with, think of it as a repeated addition. So that's how multiplication emerged with numbers too, probably, right? So multiplication is repeated addition. So that idea turns out to be totally working out for vectors as well. So two vectors added together, identical vectors added to itself, or do it 3 times. So that's what multiplication is. And then once you come up with that idea with after all, one-dimensional vectors are numbers. So then in dimension 2, the story is the same. And then once again, you can add vectors to itself as many times as you like, including pieces. Okay, so 2A is just the same 2 vectors aligned one after the other. Negative A points in the opposite direction, half A points in the same direction, but half a short, and then 0A is the 0 vector. So you can actually multiply a vector by 0 and get nothing. Well, it's not nothing, it is 0. Okay, and so then this picture is drawn on in not even on a piece of paper, kind of in the air. So if you want to think of this as dimension 3, nothing is stopping you. It will look exactly the same. So it's called a scalar product. Scalar referring to you never have to say scalar when you do algebra of numbers because everything is a number. And here you have a mixture. So that's the challenge. A mixture. C is a number, A is a vector. Okay, so and we combine them together. As you can see, it's totally we're gonna need it. We can't live without it, right? So I'm going this way. I'm doubling my velocity. How do I double my velocity when velocity is a vector? That's I multiply that vector by 2. I reverse the direction. What do I do? Well, I have to have negative A. That vector has to point in the opposite direction. So we cannot do the algebra of and stick with algebra vectors and deal with addition only. So we have to also scale and multiply them. Okay, so symbol is the same. So once again, the challenge I'm trying to, as I promised, that every time I'm using uppercase for vectors and points, and I'm using lowercase for numbers. So that might help, I hope. But nonetheless, it takes time to get used to it. Okay, so once again, a rule is very simple. When you multiply a positive number, it points in the same direction, but multiplied by the negative number, it points in the opposite direction. So the velocities once again, I'm not sure why this is thing. Yeah, okay. So if you were to speak of displacement, right? To begin with, we already understand what they are. And displacement multiplied by anything is really doesn't make a lot of sense. But this makes sense. Okay, so displacement, and let's introduce the velocity. And what is the velocity if not distance divided by the displacement divided by the interval of time? And that's the scalar multiplication because the time is a scalar, it's never a vector, and so the change of time is a number, and so then whether you divide by that little number over here, then you will be switching between displacement and velocity. And so we usually visualize things with velocities. Naturally, such as this weather map, for example. But once we are to actually get to prediction. Okay, so in this case, where does weather? If this is the map of weather stations everywhere, and it just records the direction and the speed of the wind at every location that you produce this map. But then the question might be, where will a balloon go? Okay, in which case you don't need velocity, you need displacements, and so you multiply v by delta t. The smaller delta t, the more accurate your prediction is, and then it will trace out, and then you just go, and then you do what we have done. So it will d1 plus d2. Once these are computed, we can go on and trace the path, predicted path of the balloon through this delineator. Okay. So another reason why we want scalar multiplication. That's the difference between the displacement and velocity. Okay, so high dimensions. What do we do in high dimensions? Without relying entirely on coordinates. The answer is we can still do it. Okay, so Rn. Remember, Rn is a strength of n numbers. That's what they are. So then how do we even do algebra of vectors in high dimension? The answer is in the abstract. We're doing it in the abstract fashion, but nonetheless, we can still trace the origin of the algebra in multidimensional spaces. We can trace them back to lower dimensions. Why so? Because the operations are lower dimensional. The two operations that we have discussed are lower dimensional. This is one dimensional. Look at it. Scalar multiplication is one dimensional because multiplication will never produce an extra dimension. So you just multiply and you stretch it or shrink it or maybe turn it backwards, but it's one dimensional. Addition is two dimensional. So if you were hypothetically, you were living in this case, let's say it's three-dimensional space, and you never done any algebra of vectors in three dimensions. That's not a problem. That's not a problem because all you have to do is just if you have two vectors to be added together, they will be lying in the same plane. Okay, so and then you just carry out the addition as you have known before, and then that's supposed to give you addition in the 3D. So that's how you can easily go from two-dimensional vector algebra to three-dimensional vector algebra. Once you understand that, then you can do the same thing. Even in four-dimensional space, you can still that idea still holds. They're still vectors. They're still two dimensional. Their addition is still two-dimensional entirely. So hypothetically, if you can imagine vectors in four-dimensional space, you know how to add them. You form a plane, and on that plane, imagine that a piece of paper, and carry out the addition within that plane. Okay, so naturally we're not going to do that. We got to deal with that's what we're heading. Where we're heading is the strings of numbers. So we have to do it in the abstract. But nonetheless, the visualization still remains valid. So I have four vectors on the left to suggest that, well, this might be a four-dimensional space as a matter of fact. But the algebra is the same no matter what the dimension is. Okay. Okay, so I just changing of units in another multiplication also scale multiplication is required for the third time or the fourth time. Okay, so axioms of a fine space. I think I'll skip that. I'll skip that too. Okay, so these are addition and addition is scalar multiplication. So addition is scalar multiplication of vectors when they're still given by points. Okay, so then if we're the pictures are the same, and then what else do we need to do here? The algebra is identical if we switch singles. As units is still the same. Literally resizing your diagram. Okay, so this is a collection of vectors in dimension 2, all originated at the origin. Okay, so once again, we are from the vectors that exist everywhere, and the algebra then is carried out this way, head to toe. Since we can do addition of vectors by using the parallelogram construction, we don't really need to be able to move them around as much. Okay, so any two vectors with the same origin can be added. Okay, can be added by the parallelogram construction to begin with. And number 2 is scale multiplication 2. Okay, so once again, there are no vectors elsewhere. So I'm excluding that vector certainly is a possibility. As we know, there's no problem having vectors that originate elsewhere. But here we're limiting ourselves to the only that the ones that start at the origin. So this the choice of initial point is, and it is the origin. Okay, so in which case we are, once, as I said, we are in a good place. We can do algebra of vectors. The algebra of vectors is complete. So adding, subtracting takes extra work, extra stage. Remember, but nonetheless, the addition, you do parallelogram construction, right? So when you do add two vectors using parallelogram, the end result is a new vector is still it has the same origin. Okay, so that's why it works out. Scalar multiplication is the same thing. So you can stretch or shrink. Okay, so that's why we don't really need anything else, and we can entirely concentrate on the algebra of vectors without points. So no points necessary anymore, and these are the two operations that we really care about, and they will be expanded into the rest of the course. Vectors plus vector plus vector gives you a vector. Once again, starting at origin. Okay, and then number times vector is a vector. Once again, we only referring to vectors that start at the origin, and that works out perfectly well. So we speak of what we call a vector space, and a vector space there are no points; they are only vectors, and that's an example of a vector space right there. Okay, coordinates now. That's the biggest step that we make. We add a Cartesian system to our plane. So once again, we stick it to the lower dimensional situation, and only pointing out what's going to happen shortly. So we're still speaking of the topic. It remains where vectors come from. So we're just building up towards high dimensions. But for now, what we developed, we realized how to do algebra on the plane with drawings. Then how we might project that into high dimensions. And now what actually solves the problem for us is having Cartesian system added to our plane, the grid. Okay, the origin is chosen, that it has been chosen for a while, and now we're doing coordinate-wise addition. And as you can see, whether we're doing the triangle or we're doing parallelogram, the result is the same. If you just carefully look at the what's happening with respect to x and with respect to y, they're added, right? So once again, look at the blue one, which is the sum. So if I progress 2 units from left to right with green and 1 unit with red, then the blue one has 3 units, 2 plus 1. In the vertical direction, as you can see, I'm going 2 units up and 1 unit down. The end result is 1. Okay, so that's so once again, horizontal here, the 2 plus 1 is equal to 3. Oh, okay, that's in the horizontal direction. In the vertical direction, 1 minus 2 minus 1 equal to 1. Okay, so that's addition turns out to be entirely one dimensional, entirely component wise, which one dimension at a time. What I meant to say, one dimension at a time, either x or y. That doesn't matter. Very simple. Scale multiplication, same story. As you can see here, I'm multiplying by 2, and what happens is each of the components once again multiplied by 2. So I have 2, and here's 2 times 2 is equal to 4. And this is 1, and here is 1 times 2 is equal to 2. Okay, so component-wise multiplication, just to confirm, why is it so important? Because now we are abandoning pictures, unfortunately. As we go to higher dimensions, this becomes it. We don't have any pictures to plot, and so all the algebra that is to be executed will be executed with numbers. Okay, so let me try to, so that's the vectors in our end. So let me try to summarize what we've got here. So we have this, let's say Rn, n is equal to 1, 2, 3. What is it? It is the observable physical space. Okay, so that if we are stay there, then we have points, and we have geometry. And what we also have developed, we have vectors in the vector algebra. For the time being, that's sufficient. And then what with the step that we also have made is we add a coordinate system, yeah, add a Cartesian system, or let's say just coordinate system. which gives us what? Then Rn now is with strings. It's not an observable physical space, at least on a piece of paper. Strings of n numbers. So it's entirely abstract. Okay, so there's nothing observable about it. It's very abstract. Literally all possible strings of n numbers. That's what this space is supposed to be. Naturally, in dimension 3, I just demonstrated to you that works out perfectly well. The match of the algebra of vectors and the geometry of points works out perfectly well. So then I can say that we have geometry. We have geometry here and algebra with those formulas. Okay. And there's a match, and we can go back to as a way to visualize. Naturally, once again, this only works out n is equal to 1 to 3. Once n goes to beyond 3, what happens? What happens? Well, this is gone. Okay, so this is gone. And larger than 3, and so we're stuck with what's on the right. So strings of n numbers, and then geometry, the algebra of vectors, for example, is done component-wise. Geometry, we have those formulas. Remember, formulas for measuring distances. You realize at that point that the space is not physical anymore, so we have choices. I didn't indicate any other choices for algebra of vectors. I don't think it makes sense. But geometry, we made at least 3 formulas, L2, L3, and the other one, different geometry for it. So that is the challenge. That is the challenge, that everything is you can still try to visualize, but under the assumption that you're losing a lot. So because you cannot visualize anything higher than dimension 3. Oh, so all right. So let's go over that next. Okay. So all right. So let's read. So in lower dimensional case, we had this visual space. We did the algebra, we did the geometry, we did the Cartesian system now. Okay, to those 3, that's literally a coordinate system that you add. And then in n-dimensional space, there is nothing but the Cartesian system. In fact, it is the Cartesian system, right? So we do not add like to the space we live in, and then we add coordinate system so we can know where we are. It is the coordinate system, not because there's nothing but itself. Rn is the coordinate system itself. There is nothing else. So we use the former to make sure that the approach to the letter makes sense. We just what we have started doing. Okay, so once again, if we look at points, we subject them to the geometry, and then there are also vectors there. They will be subject to algebra. Okay, so the difference really now, let's quickly review, but now without fewer pictures, but with more numbers. And so once again, that's what it means you have 2 points, you create a segment between them, you call it PQ, and then you ship that segment to the origin in order to produce, at that point you have a vector. So this A is a vector. And so you just have 5 units in the positive direction. Okay, so then as we can see, as we discovered, the addition of vectors is in dimension 1 is adding components. In dimension 2, it's also adding components. And once again, the operation is the same. It's before we get to addition. Here's, as you can see, 2 points. The idea: 2 points, connect them by segment from P to Q, and then shift the segment to the origin. Okay, so we did it in dimension 1, and now we do it in dimension 2. Okay, so in dimension 3, what's the difference? The same thing. So by the way, let's look at the numbers, right? 2 and 7, and then I end up with 5. So because these are only numbers, then the numbers that matter is 2 and 7 are locations. The displacement is 5, and so the vector is 5. So A is literally equal to 5. Okay, so that vectors for P to Q is 5. Now you go to dimension 2, and you have points. This time they have 2 coordinates, but nothing, the geometry remains the same. I go from P to Q, create an arrow, shift arrow to the origin, and then examine it. What do I have? What are the components of that vector? And the answer is the change in x and the change of y. So in X, we change from 2 to 1. Look at it. From P to Q, we change from 1 to 2 rather. And then in the vertical, we change from 1 to 5. Okay, so which means that then these are from 2 to 5. From 1 to, hold on, it looks like a typo. From 1 to 2, oops. Match these. From 1 to 2, so it's 2 minus 1 is 1, okay, and with respect to y, it is from 1 to 5, from 1 to 5. From 1 to 5, so this is 1, and so this is 4, okay? So then my vector is 1, 4. As you can see, once again, I'm using this to distinguish between points and vectors. I'm using the triangular brackets again. Okay, so once again, points will be subject to geometry, vectors subject to algebra. Okay, so what happens in dimension 3? The same idea. Now we need less and less pictures. But nonetheless, we still can do it. So let's do it. So we have points P and Q with coordinates x, y, z. Q with coordinates x prime, y prime, z prime. We draw a vector PQ, and then what are the components of the vector? Okay, it is the difference of the three. As we move from P to Q, what happens to the three coordinates x and y? And so we're looking at subtraction. So we build this box, and the sizes, the dimensions of the box, all will be the coordinates, the components of my vector. So as you can see, we're moving from left to right from P to Q. And so once again, how much we moved in the one direction, that's this towards us, that's x minus x prime, y minus prime, y prime that way, and down is x minus x prime. So there you go. I put these three numbers without specifying what they are this time, and I have, so once again, triangular brackets, x prime minus y, x prime minus x. Remember which one point is first, which one is second, and that gives me the new vector. And then once you did it three times, we did it 3 times, you jump to a dimension, and that's the definition. So now my vectors are vectors once again made of 2 points P and Q, and then how do we create a vector? We give it components. So in this case, we'll just speak of components before notation is put forward. We'll just say it is once again a string of numbers. So string of numbers, subtract component wise, coordinate wise, and that creates a new string of numbers. Very, very simple computation. But because they dot, these are actually sequences. So sequences, it's not an infinite sequence, but nonetheless it's sequence. And we are doing that kind of operation that you must have done in calculus, subtracting sequences, subtracting functions. So you do it one value at a time, and then you have a new one. So you have it from this sequence, 2 sequences, we have a new one. From those 2 functions, we have a new one, and then we just combine them together into a string of n numbers. But this time we put brackets on at the end, at the beginning, and the end, so that we're holding them together. Okay, so that's my vector. Okay, that's all there is. Okay, so and then naturally, so that's entirely abstract as far as we're concerned. Where's the picture for this? There is no picture for that. You somehow have to connect these to the n-dimensional space in your head. Okay, so that's notation. Alternative notation is very important. Is the column. So the vector with the braces, in fact it's preferable. Notation is the column. It just takes too much space, and that's why we abbreviate it with the triangular brackets, so that it will be a string rather than a column. You'll see why columns are preferred. Okay, so once again, this is the operations. Second, algebraic operations. Okay, so we've done this before. Once again, the vectors. Once again, so you have to take all of these pictures and imagine that they're n-dimensional. Fortunately, this is really where the point is. Imagine that there are no pictures, but these are the computations. So this is Excel, and Excel doesn't care how many numbers you give it. It cannot visualize them anymore. So if you have more than 2, but nonetheless, if you have a string of 50 numbers, it will do addition of 50 numbers one at a time. No trouble whatsoever. So once again, you have to visualize somehow in n-dimensional space. That's what big vectors look like. So this is 2-dimensional. Imagine 3-dimensional. Okay, have you imagined 3-dimensional vector space? What does it look like? Also, there's an origin. So here, there are more degrees of freedom. So imagine the same thing, but only some vectors are pointing at you. Okay, and some vector away from you. So it's rather than going in these directions within the plane, you also the third dimension is utilized, and so it's like a ball of vectors or an explosion of some kind. So when actual explosion goes in all three dimensions. How do you do four dimensions? That's for you to try to figure out. That varies from person to person how well you can visualize high dimension. Okay, so that's the point, and then OP is the same. So that's replaceability. It suggests that this is maybe it looks simple, but really there's a point there. Even though the components are the same and coordinates are the same, nonetheless we have the two different entities. Okay, so the entities of point with parentheses, and brackets give me the a vector. So once again, remember we were doing algebra with vectors and not with the points. Okay. So addition, once again, either it is a column or it is a row. Addition is done kind of component-wise, as simple as you can imagine, except in dimension 3, you have 3 times much work as you would do if you were dealing with numbers. In dimension n, the same. Once you do 3-dimensional, that's what you do. You do it component-wise. That kind of stands in the way, but nonetheless, you just imagine that there are n of them. If you want visualization, that's something that you go back to calculus. When you did addition of sequences or functions, that's what happens. Literally, you visualize a vector as say in this case 20 numbers, and then twice, and then you just add them together. How? Just literally the length of A added to the length of B, and then you end up with two kind of a what do you call it, like a stack on top of the other. Okay, so that's your addition. Does not look like a vector. This does not look like a narrow, right, at all. But that's the price we will have to pay when we go into high dimension. Scale multiplication, same story. Once again, component-wise. This is once again going component-wise and multiply by the same number, same number. So that's the how we write it. Once again, we do not refer to OP anymore. That's what we're trying to switch from points to vectors. And finally, that's what the multiplication looks like if you visualize your vector as a string of numbers, as a string of bars, for example. Okay, so addition visualized by placing one on top of the other. Scale multiplication, you literally stretch every one of these bars. So in this case, 1.3. So those bars become longer, and you have a new sequence of numbers, which is nothing but a new vector. Okay, so we'll look at examples next. Just to make sense, the algebraic operation in n dimension. What's the point if we are to forget about lower dimensions and the physical space? Here it is. Here I have 2 portfolios, and literally I have 10,000 stocks, and I own some of each of the portfolios include one of this. Different number of shares in each, and then if I'm were to merge 2 portfolios, then literally I do addition one at a time. That's it, as simple as that, indeed. So how do I merge the portfolios? I just take how much a stock I have. For each stock, I do addition of the number of stocks in portfolio A, portfolio B, whether they are not. These are, I put the dollars here, but really it's not. Doesn't have to be dollars. This could be number of shares, right? Could be dollars, could be number of shares instead. Makes no difference, because in fact, probably number of shares is a better way to explain it, because non-homogeneity of these vectors is an important thing to remember. So they do not have to be in the same unit. So dollars, I just make it convenient, but the number of shares is as far as algebraic operation is concerned, you never mix up Apple with Microsoft, and so you do addition for Microsoft here and for Apple there, and so they're never whatever their prices are. It makes no difference when you merge. Okay, so literally addition. Scale multiplication also, if I want to double my portfolio, that literally every one is multiplied by 2. So that's the operation. That's a little bit of Excel here. So here, non-homogeneous holdings, as it suggests, what if you can have commodities, and commodities measured maybe in dollars if you want to, but really the reality is how much of these you hold in the literal sense. So you have tons of wheat and barrels of oil, and then you have here these are the dollars and these are yens. Okay, so you don't want to really think about them as dollars, of yen as dollars, even though there is a exchange rate. Nonetheless, it changes every day, so you're treating them separately, but nonetheless, your portfolio then is made of these non-homogeneous quantities, each one for each of the components. Okay, so I'll stop here. So see you next time.